You can speak out. Okay. Because I cannot see anything in the chart, not there in the screen. Okay. The title today is about discretization of integrals on compact matrix measure space. The date is wrong. I'm sorry. Okay. This paper is a joint work with Professor Martin Blumen and Professor Van Dijk. This is the table of content. I will first come to the motivation. Discretization is an important step in making a continuous problem computationally feasible. A prominent example is seeking effective ways of approximating the integral by the weighted summation. This lambda j is the weight, and the X row is a compact matrix space. They can be So this discretization process can be considered as the discretization of probability measure on X. Actually, it works for any measure. Here we just normalize the measure and make it as a probability measure. The formula lambda n is called curvature formula with node Xi and with lambda. It's called positive curvature formula if all lambda j are greater or equal to 0. The error of such approximation is measured by the following quantity. Just take the supremum of this phi is a function defined on the real line, and the rho is a matrix on X. Mu is a measure on X, and so the error is measured by taking the supremum of all phi rho in W. This W is a function space defined on X. We can further optimize this error by studying the infimum of all the lambda n with taking the infimum through all the weights lambda j and all the nodes Xi. Using the Bernstein inequality in probability, we can show that for any continuous function f, and Xi1 to Xn are independent random point selected uniformly on the unit sphere, then there exists an absolute constant Xi1 greater than 0, such that this inequality holds with probability greater or equal to 1 minus 2 times e power negative Xi1 t square. The proof of main result in this paper is mainly follows from the paper of Bogan. Okay, then we come to the main result. Let omega rho be a compact matrix space. Open bound and closed balls are denoted by this and this respectively. A path connects two points xy in omega is a continuous mapping gamma from 0 to 1 to omega with gamma 0 to equals to is x, gamma 1 is y. This gamma must be a continuous mapping. We say that a matrix space omega rho is path connected if every two distinct points in omega can be connected with a path. As we all know, every open connected subset of Euclidean space is path connected. Given a subset A and a point X in rho, define the distance of XA by taking the infimum of O y in A of the matrix rho XY. Okay, the first main result is about regular partitions on compact matrix space. Measure mu on omega is called non-atomic if any measurable set A in omega with mu A greater than 0. There is a measurable subset B of A such that mu A greater than mu B greater than 0. For non-atomic borrow probability measure mu on omega, we have this property. If A0 contains in A1 contains in omega, mu A1 is greater than 0, and for any t between mu A0 and mu A1, then there exists a measurable subset ET contains in A1 such that the measure of ET equals to T. Let omega rho be a compact path-connected matrix space its diameter of omega equals to pi. Let mu be a non-atomic Borel probability measure on X, on omega, and n greater or equal to 2 be a positive integer. Assume that the inequality about the measure, that is the unit ball, any unit ball with diameter delta over 2 is the measure of n, it is greater or equal to 1 over n. This works if this works for all x in omega, and hold for some delta greater than 0, then there exists a partition of omega R1 to Rn such that first Rj are pairwise disjoint subset of omega. Second, for each j between 1 and n, Rj, the measure of Rj mu Rj equals to 1 over 1, and diameter Rj is less or equal to 4 delta. The above theorem with constant depending on certain geometric parameters of the underlying space omega rho mu is probably known in general setting. Like when omega is the unit sphere SD minus 1, or SD, it doesn't matter. There are some irregular partitions on that. But the constant here pairs are always dependent on the dimension d when omega is a unit sphere. But our result here for is an absolute constant. Absolute constant. It doesn't. It's not about the. It's not related to the dimension of the unit sphere. Yeah. Okay. The second main result is about discretization on compact matrix space. We first give some information. Let X rho be a compact matrix space with matrix rho and diameter pi. For X and AB between 0 to pi, we said that EXAB is that for any X in y in X, rho XY is greater or equal to A, less or equal to B. Here it's like a tutor, or it's like a, let me see if I can write something. Yeah, okay, I can. Okay, it seems that I cannot write. Okay, oh yeah, this EAB is like a ball, and then kick out some small ball inside. A ball of diameter B, kick out a small ball of diameter rho A inside. Yeah. A partition of AB consists of finitely many pairwise disjoint subset. Then here we give the conditions of phi. Let T1 to TL be a partition of the interval 0 to pi, and R real number R be an integer. We say that phi, continuous phi, belong to the class SR if there exists an R-dimensional linear subspace VR of Cx, such that for any x in X and each j between 1 to L, phi compose with the matrix rho when it restricted on the set E x tj minus 1 to tj. There exists f in VR. VR is a R-dimensional linear space. So there exists a function f in VR such that f restricted on the set Ex t minus 1 to tj minus 1 to tj is equals to phi composed with rho restricted on this set. That is, phi composed with rho is a piecewise, its piecewise belong to VR. Like when VR is a polynomial space, then we can say that phi composed with rho is a piecewise polynomial. Let mu be a Borel probability measure on X, satisfies the following condition for a parameter beta greater or equal to 1 and some constant C1 greater than 0. Condition 1 says that for each positive integer, there exists a partition of X such that each xj, its measure is 1 over n, and diameter of xj is less or equal to delta n. This, according to our theorem proved before, this condition holds automatically with C1 equals to 20 pi if the matrix space X is path connected, and mu is non-atomic Borel probability measure on X. Satisfies the condition, satisfies the formula 2. Yeah. Then we come to here phi. Okay, that phi is a continuous function defined on 0 to pi, satisfying the ellipsis condition, and it belongs to a class SR. This SR is what we said. It's like when phi composed with rho restricted on the set E, there exists a function in the R-dimensional linear space. It's equal to that F restricted on the set. Yeah. And belong to SR on some compact matrix space. Let mu be a Borel probability on X satisfies the condition A and that following condition. That is u ex tj minus 1 to tj. The measure of this set less or equal to C2 dirt. It's like that. Okay, it's like, for example, when X is a unit sphere, we can slide X by the latitude. Yeah, I think it's latitude, and the boundary of each latitude, the measure of the boundary of each latitude can be controlled by C2 dirt. It's like that. Let phi in C, phi is a continuous, yeah, mu is a probability satisfies the above condition A and condition B. Then for each positive integer n greater or equal to 2, there exists points y1 to say in X and negative numbers lambda 1 to lambda j, they greater or equal to 0, such that their summation is 1. And when we take in this error can be measured by the C3 in power negative 1 over 2 minus 3 over 2 beta times square root of log n. Here C3 is a constant related to the L beta and C1, C2 in above conditions. Okay, another result comes here. Let X0 be a compact path-connected matrix space. Phi is belong to SR, and its ellipsis condition satisfies the ellipsis condition. And let mu be a non-atomic Borel probability measure defined on X, satisfies the condition 2. Assume in addition that condition B in theorem 2.3 satisfied, then for any L infinity function f, it's bounded by 1. It's L infinity norm bounded by 1, and each integer n greater or equal to 20. There exist points in X and real numbers lambda, such that we have this boundary. Here, we cannot guarantee this lambda j greater or equal to 0. or its summation equals to 1. Okay, the final result in this paper is about discretization on finite dimensional compact matrix, compact domains. Let X and the norm be a finite dimensional real normed linear space. This norm is not necessarily a Euclidean norm. But omega contains in the unit ball be a compact subset of X. This omega is not necessarily connected. Mu be a borrow probability measure support on X on omega. We'll assume that the probability measure mu satisfies the following two conditions. First is that the measure of ball with radius delta, it can be controlled by the C4 inverse delta power beta and C4 inverse delta power beta. C4 delta power beta for any delta between 0 to 2 and for any x in omega. Second condition is that if there exists a constant such that this is also the bond, the bonds of measure, the bond measure can be controlled by C5s. Let phi also here phi satisfies the ellipsis condition. Assume that there is a partition of 0 to 2 and the translation invariant linear subspace XR of C omega. Its dimension XR is R, and EJ is the bond such that X between the norm of X between TJ minus 1 to TJ. And phi composed with the norm restricted on EJ. There exists some FR. There exists some F in R dimensional linear space XR such that phi composed with the norm restricted on EJ equals to this F restricted on EJ. And let J in L1 is function such that its its L1 norm is normalized by 1. Under these two conditions, we prove the following result. For each positive integer n greater or equal to 2, there exist points y1 to yn in omega and real numbers lambda1 to lambda n, such that we have this estimation. This beta is the condition we defined above. It's about the measure. The constant Cx depend only on dimension x and the properties of x. Here we give one example. It's about the discretization of the unit sphere. Let x equals to SD be the unit sphere of Rd plus 1 equipped with the normalized surface Lebesgue measure mu d and the geodesic distance rho xy equals to arc cosine x dot y. We have the result. First is that the measure the unit ball, no, not the unit ball, the ball with diameter, the ball with radius delta n, the measure of it is greater or equal to 1 over n. With delta n, this can be calculated out. Okay, lemma 2 is about like the measure of the bond. U for any fixed x for any y between lies in the set that rho xy is greater or equal to t minus delta to t greater or equal to t plus delta. The measure of this is less or equal to 3 or 2 square root of d times delta. As a consequence of theorem 2.1 and lemma 3.1, we first have this partition that there exists a partition of SD such that each Rj are pairwise disjoint subset of SD, and each RJ they have measure 1 over n. Diameter RJ is less or equal to 40 pi times n power negative 1 over d. Again, the main point here lies in the fact that n power 1 minus d times maximum j, diameter of RJ, is independent of the dimension d. Theorem, the above theorem with dimension depend on the upper bound. Its dimension dependent result in the upper bound can be found in reference to. Yeah. Okay, from the theorem 2.2, we have the result. Let's phi be a piecewise polynomial of degree at most r, and satisfy the ellipsis condition. At MR equals to MRD, denote the dimension of the space of all spherical polynomials of degree at most r on SD. J at L infinity function such that its norm is bounded by 1. Then for each positive integer n greater or equal to 20, there exists points and real numbers such that we have this estimation. It's hold for all x in SD. And this is the reference. Thank you very much. It's not in 1 hour. I'm sorry. Yeah, if you have any problem, you can ask me. Thank you.
Yeah, thank you, Yeli, for this presentation. Are there any questions from the audience?
Yeah, I would start directly. Could you explain shortly what the role of this x is? So somehow the form of your integrals is kind of special to me, right? So.
Oh, you mean this x?
Yes. So the original problem you are looking at. So is there a motivation for this specific type of functions, or is it What is the reason for this kind of function?
The motivation of this main result is only because in real life, like in neural network, or like we cannot say we can if we want to find an integral of a function, we do not know its real forms of this function. We can only pick some point from the real world. So if we want to figure out the integral of a function in real life, we can only do the weighted summation of this selected point. So finding a good ways to
But still, I really don't get what this x means. So you want to say that the form of functions you are considering ignoring this x, this is just a matter of your formalism, right? So actually you have a function such that there exists a point such that if you go away from this point, then your function is supposed to be continuous, right? Basically, for me, this does not really look like a big assumption, but yeah. Okay, so
you mean
whatever. I don't really get what the special role of the x is, and also if you go to the sphere, for example, is every x then the same? Is it the same way of important for every x, or is it? I don't. Point.
Like here.
Yeah, I missed it in the beginning. Sorry.
It's hold for all x. Yeah, it's hold for every x. The result is independent of. It's hold for every x. I still cannot get your problem. I'm sorry. Can you?
No. So why do you write down the x? What is your reason for introducing this x? Because all your calculations, all your results are independent of x. So what is that? There must be at least a motivation for writing down things like that, right? Is it that you want to understand rank 1 functions, or what is the point?
Well, actually, this is this process is like a neural network. It has applications in neural network. I still cannot.
So just a comment. I was asking I was asking me this question from the first slide of your talk. So just for a comment for the future, you should maybe give a comment on that. So just for people to follow. I was asking me the whole time, is the special role for X? What is X for? Give me an example where X is special.
You mean
and then at the end, nothing like that is there, right? So for me,
you mean the domain like X here? You mean here? Like do you mean for this X?
Yeah. So you probably, it must be on one of your very first slides. So I'm sorry if this is offensive. Please don't feel offensive. I really want to understand the problem because dimension independent bounds are interesting to me, right?
Yeah.
But at some point you formalized your problem. That probably it's here already, and there is an X. And in the first line there is an X. So what is X? And yeah, I understand. Maybe there is something related to neural networks. I'm not an expert on that. No, not big X, small X.
Small X. Oh.
Why is there a small X? I don't get it. And do the weights and the Yj depend on X or not? And so on and so forth. So there are many questions related to that.
This Yj is not dependent on X. This Yj is it's just random point on the space X. It's the Yj selected. The Yj selected here. It's not dependent on X here.
Okay. So the weights also don't depend on Y. On X, man.
Lambda j is so with lambda j, it's not dependent on X. This is
okay.
With lambda j, it's also independent of Yj.
Then just a comment, and then I'm done. If the Yj and the lambda j do not depend on X in whatever setting, you should mention that. In the biggest form you can do that, because that's a specific point of your problem, I guess, right? So you have an integration rule where you can shift around with this distance thing, so you can change the X and nothing changes. So your quadrature rule is the same and so on and so forth, and still you have the same upper bound. This would be an interesting fact.
Yeah. This because the main idea of this paper is just like first for every X we can. For every small X in the space X, we can get the bound, and we can show that the bound, we can show that the in the Bernstein's inequality, we can show that the give me a second, let me find. For every fixed X in small X in the space X, we can show that there is a probability, there is a set Jx with probability. Can be controlled by something. We have this bound. Then because we can divide the space X into n small pieces, pairwise n small pairwise pieces, and each pairwise pieces can be controlled. We have that result, and then for each pairwise pieces, like I denote as xj, for each xj we can pick a point. Because each xj, its diameter can be controlled. That's why we have the ellipsis condition. We can pick a point in each xj, and for any other x in this xj, because it's in a small ball of this xj, then we can use that bound to approximate that each point in the to make that each bound in the xj hold with this probability, and then we, because like we take small xj in the partition xj, and then
Sure, but you could easily write down your example in the way that you say you are integrating rotation symmetric functions, right? So rotation in the sense of your metric. So if your function is rotation symmetric and the one-dimensional function involved is Lipschitz or whatever, then you get the bound, right? That's a way to write it down, and this is a way to write it down without any X. So okay, so I think I'm done. But by the way, this formula here might be, so that the theorem itself might be easy not easy to believe, right? Because there is no norm on phi specified here. So is it? I'm quite sure that there's something missing on the right-hand side, or some Lipschitz condition or whatever, because otherwise, just taking the supremum over all continuous functions would clearly disprove
if
your
there
result.
is no Lipschitz condition, this does not hold.
No, you need a quantitative.
But I think the
function.
Lipschitz condition is hidden in constant C3, no? So constant C3 involves. Okay, so
you mean
have
this
Lipschitz
Lipschitz
1.
condition?
Okay, Lipschitz with constant 1.
Okay.
Okay.
Yeah, there's also this class S, right? So it's like a piecewise.
Yeah, piecewise piecewise in R-dimensional linear space. Oh, sorry, I cannot write here because I use a computer. If I can write here, I can expand the process more in details. I'm sorry, because I use my computer to share the slides.
Yes, so I think maybe some of the motivation comes from if you take a neural network and it has a real U function, right? It's a piecewise polynomial.
Yeah.
Then you have these nodes, and then I guess nodes have something to do with the coefficients, with the specific coefficients your network has been trained for. So maybe this was part of the motivation. But then I don't really understand what the continuous integral means. So Mario had an issue with x being in this.
You are confused because we already have the Lipschitz condition. So you say we do not need the continuous condition, right? Do you mean that?
Oh no. Yeah, I'm not. Yeah, I'm not an expert. I'm just trying to understand what. So you have a continuous function. So if you go to one of the first slides, which you then discretize, right? So then I can sort of understand that the discrete. Yeah, maybe a little bit further when you.
You mean here?
When you write your okay, can we go to one of the estimates?
The main result part.
Yeah, just one of the estimates. I think that's a good good place to look at.
Yeah, here.
Yeah, right here. Yeah. So okay. So maybe the motivation for something like the sum, right? So you have this. You're estimating the uniform norm. So you're approximating the uniform norm, some continuous, some potential of some measure, right?
Yeah.
So if you, right, and then, okay, so the finite sum is like, could be some kind of neural network thing, but then what this means is your ground truth, the function that you're approximating with your, so to say, neural network, is of this form. So I guess I would be interested to understand why the motivation for this class of, I guess I can annotate on your screen. Yeah, so it'd be interesting to understand what is the motivation for this expression, right? So what is, so okay, this is maybe neural network.
Yeah, this is like neural network.
But
yeah.
what is this, right? So somehow there is an object in the nature that comes in this form. You're trying to approximate it. So I'd be interested to understand, okay, what kind of objects come in this form? So
okay. About this question, I didn't. Give me a second. Okay, I'm sorry, I didn't consider about this problem.
I'm sure there's some motivation, but it's just interesting.
Yeah, I didn't consider about this problem before. I'm sorry. But I will try to figure it out later.
Okay, let's see. Any more questions, comments we have?
I'm very sorry about this.
No, it's all good.
No, it's fine. I have a question.
Okay.
so at the end, you were showing that the sphere works as an example for your theorem, right?
Yeah.
So something I was just curious about was that, so right, one of the conditions for your whole for to be able to do what you're doing is, right, you somehow have to have this, you have to somehow have like these bounds on the measures of the annuli that appear, right? Different annuli of different radii. So it works for the sphere apparently. Are there general classes of domains that you know it works on, or also are there some domains that you specifically know it doesn't work on?
Oh, doesn't satisfy these two conditions. You mean?
Yeah. Are there any interesting sets? Are there any interesting domains that somehow don't satisfy the requirements in order to do this to basically satisfy your results? Or the alternative question there are, so aside from the sphere, what are other spaces it does work on?
Yeah, I didn't check other domains. Maybe I think, yeah, I didn't check if it's, I didn't check other domains
Okay.
that it doesn't work.
Okay. It was just curious. So like for projective spaces, the ones that are 2-point homogeneous, do you have any idea for those? Because usually those work about the same as the sphere.
Oh, I didn't check that.
Okay.
I'm sorry.
Oh no, it's fine. I'm asking because I'm curious. That's all.
Oh,
Thanks.
yeah. Thanks for your question. I will consider later.
Any further questions or comments?
One short thing about the sphere, I was just wondering, the X really plays no role there, right? Because the domain is the same for every X, and you have a uniform bound over all phi, and so on. So the sphere is really no good example. You should have something that is kind of non-uniform in a way that this X really plays a role, right? Here it's just so introduce additionally a maximum over all functions phi, having some Lipschitz condition or something, it's written there. And the whole quantity does not have anything to do with X.
Oh, you mean the small x here, right?
Yeah, again, yeah, the small, I'm still wondering what is should be what is supposed to, right? But just as a comment, for the sphere, there's really I think I can, if the things are proven without X, I am not an expert on the sphere, but if the things are proven without this X, then I can prove it with this X easily. Because it's everything rotation invariant, right?
Oh yeah, this result actually holds that if there is no X in here, it's also hold that use burst as inequality, we can obtain that.
No, but then your result is an easy consequence of this. That's the only thing I want to say, because everything you are writing down here is rotation invariant.
Yeah. Oh.
So the sphere is just not a good example for your, maybe, or I get it wrong. Please correct me if I'm saying something wrong.
I actually might disagree with you about that rotational invariance, just because so G is chosen to be an L infinity function on the sphere, but
the
that
G,
doesn't
yes,
have to be rotationally invariant in any kind of way. So all of that has to be concentrated near like just one side of the sphere, and then you lose the rotational invariance, I think.
That sounds right.
So some dependence on X here then.
Just to understand your point, Ryan, the G is correct. Yeah, there's something, but now the G confuses me even more. What is if G is just the indicator function of the rational numbers or something, of points with rational coordinates? No, really, it's an L infinity function, right? But then the
Yeah.
whole problem here is kind of, if you change x, then the quadrature rule could give you something or give you 0, but the integral is in any case 0. So what is all this about, right?
Huh.
So now I'm quite confused about the function g. So I can't get better.
I
Maybe
see,
I should
like G-
look at the paper.
G works as a weight here.
Sure, but your weight
Right.
could be 0. Or
Oh, you
indicate a
mean
function,
G could
complicated
be.
one.
Oh, you mean G could be 0. Okay, give me a second. Let me give me a second.
No, but
Oh
that's
yes,
okay. So
actually
just
this
take-
lambda J is dependent on G. This with lambda J depend on
Oh.
the choosing of this lambda J depend on the function J. It's not works for all J in L infinity. So if when J should be 0, then I think lambda J.
Yeah, all lambda j's with 0. That's it.
Yeah. Just lambda J, the choosing of lambda J depend on the J. So it's not works for all J. So because we didn't, you can see that we didn't take superminimum of all J in L infinity.
No, I would just want to say already for a fixed g, I'm a bit confused, but I need to check your paper, I guess, because let me put a little bit more advanced my argument, right? If g is the indicator function of points with rational coordinates, for example, right?
Yeah.
Then the quadrature rule is 0 whenever all points are irrational. So whenever x is irrational in some sense, but if x is rational, right? Then there are only rational points, and so I have the feeling that this somehow is strange. Is it? Am I completely wrong? Do you need only the L infinity assumption here? Yeah, for the g, is it correct? Sorry. Please ignore me. I have to check the paper.
Well, so wait, so it's saying, right, you choose the G, and then once you've chosen the G, you should be able to choose the points and the coefficients, the lambdas, such that you get this bound.
It's a point and the point and lambda depend on J.
Right. So it's not something that works just so you're not choosing anything that works for all G. So potentially that would mean that, yeah, you just have to, in the case that you're describing, right, you would just need to choose all your lambdas to be 0, and then you would get what you wanted, right?
No, but you can choose x freely, right? And I say that if there exists points with this property, then I can, this xi j here, then I can choose all xi j to only have irrational numbers in it, just because of the continuity argument, right? So all xi j are irrational, g only uses irrational points, whatever, right? But still I can choose free this x. And I somehow have the feeling that under the condition we have, that this is a heavy argument. But as I said, it's just stupid stuff I'm telling you. I just want to understand it.
It looks good to me, right? So you're given the G, but you're not going to prescribe Xi either. So the Xi's and lambdas, so there is a machine that spits out the Xi's and the lambdas. What you put in the machine is G and phi, etc. Right? Yeah. So it looks good. Yeah, but
I believe you. Sure. Sorry.
Yeah, so it's not a quadrature, right? It's not a quadrature rule. It's some kind of approximation argument.
Yeah.
It's not a quadrature which says here's a property which is uniform over entire space or something like that.
Anyway. My example was stupid, because in this case we would just take lambda to be 0, as Ryan said. Sorry for that.
Yeah. Mm-hmm.
Oh, it's good. It's good to be asking these questions, right?
Yes.
Yeah, you were saying that some of this could be used for neural networks. I'm relatively unfamiliar. Is there like, I guess what's the basic idea of what happens with neural networks? It's also fine if you don't have an answer.
I forgot part of things. I'm sorry, I forgot part of things. I didn't prepare about this part.
No, that's fine. That's fine.
I'm very sorry.
No, that's fine.
I have a short question as well. Do you know something about the lower estimate?
Huh?
Do you know something about the lower estimates of?
Zonal function. Yeah. Oh, yeah. Oh yeah. So yeah. Thanks for mentioning. Yeah, for the zonal function, they use the oh, I forgot about that part, but I remember for zonal function, yeah, they release like the inner part, like the yeah. I think what's its application in neural network is like about zonal. Is that zonal function?
No, I just meant do you know just because he has like only upper estimates, but do you know something about the lower estimates for some for such estimations?
Previously I know something, but I forgot about this part. Yeah, I remember that this part related to the neural network is like zonal, something about zonal what? I forgot. I'm sorry, I forgot about this part.
Okay. So that's all good.
I will check this later.
Yeah, we can obviously interested participants can talk to the speaker later again. I think our speaker has a class to teach after this, so we may not have time for any more questions. So thank you all for coming. If you want to stay around and socialize, you're always welcome to. And I hope I'll see you all next week.
For your questions.
Thank you very much.
Yeah,
Thank you, Yeli, for
Yeli.
the talk. Some good discussion.
Thank you. Okay. Then I will leave now. Thank you.
All right. Yep. Thank you.
Thank you. Bye.
Sasha, do you want to stop the recording?
Good point. Yeah, I forgot to do that part, right? Where I have to stop and then ask again. Yeah, I had an